Okay, the first way we can mix it up a little bit is by using a mixture of weak acids. As you read through this, the key here is if you have a mixture of acids, only the one with the largest Ka will contribute to the hydrogen concentration. If you have an acid sitting here, just any old general acid, as it dissociates, it produces your hydrogen ions and the anion. This hydrogen then is present for every other acid that's already in the equilibrium or already in the system, and will force the equilibrium back the other way for the rest of the acids. So whatever hydrogen is produced by the one with the largest Ka is the amount of hydrogen that's present for every other acid in the system. Okay, no matter whether it's a group of different acids or whether it's multiple dissociations of a polyprotic acid, which will come a little later. So calculate the pH of a solution that contains HCN and HNO2. Not sure why those are separated. So we have to pick the one with the highest Ka. We have, this one is, the 10 is on the next line. This one's 10 to the negative 10, this one's 10 to the negative 4, which means the HNO2 is by far my stronger acid. That's the one I'm going to work with. So HNO2 goes to H plus and NO2 minus. At this point, I'm going to solve the beginning of this just like the previous question. Using a rice table, 5.00 molar and 0. You try it, watch if you need to. Plug it into my Ka expression. Okay, then I can cancel out the x, or at least try to. So 4 times 10 to the negative 4th times 5 is 0.002 equals x squared. And that gives me that x is 0.04472. I should check my 5% just to make sure. 5 times 0.05 is 0.25 versus 0.0447, so that is definitely okay for me to do. Much smaller. To get my hydrogen concentration then, X is equal to my hydrogen concentration, so pH will be negative log of 0.044. We've got 3 sig figs here, so I'll go ahead and bring all 4 values. 0.04472. And that gives me 1.349 for my pH. The other part that this asks me is calculate the concentration of the cyanide ion. That is part of the other equilibrium happening at this time. So what happens here is I need a new equilibrium expression and equation. So the HCN yields the H plus and the CN minus. The Ka this time is for HCN. So that would be H plus CN minus over HCN. I don't remember if you heard me say this a few seconds ago, but the hydrogen concentration for every other equilibrium happening in this beaker now comes from this first dissociation that we created. So the HCN, go back up to the equation, was 1 molar. So we start off, he's 1.00 molar. The hydrogen was created by the first dissociation. So that's equal to the X value, or to the hydrogen concentration, is 0.04472. And then we don't know the cyanide concentration. So if we take a look at our expression, we know Ka, we know H, we know HCN. We just have to solve for this missing piece. Ka is 6.2 times 10 to the negative 10. Hydrogen is 0.04472. Cn we don't know. HCN is the the beginning concentration here, so 1.00 molar. And we just solve for the Cn. Okay, and then cyanide concentration is 1.3864 times 10 to the negative 8th molar. Let's take a look at significant figures. We've got 3 here. This is a constant, so it shouldn't necessarily influence it. So we should have 1.39 times 10 to the 8th molar cyanide. Good job. Okay, exercise 3, continuing the pH of weak acids and bases, is again very similar. This time, instead of looking for pH, we're going to be looking for percent dissociation. So how much has dissociated out of the original amount? Process starts off the same. We have an equation or a reaction that is a dissociation of an acid. We have the Ka value. That's the one you'll memorize by the time we're done here because you'll do it so much. Then we look at the original concentration. 1.0 molar, none for the products, minus X and plus X. Set it equal to the Ka. Relatively large concentration, relatively small Ka. Let's try canceling it out. In this case, it's as simple as this is multiplied by 1, so it's the square root of the Ka. So that gives me X is 1.34, times 10 to the negative 3. I need to check my 5% rule. So 0.05 times 1 is 0.05 in comparison with 0.0013. So that works out. And I can use the, I can go ahead and cancel it out of there. So that means I've got the hydrogen concentration, I've got the acetate concentration, and I can get the acetic acid if I want to. But I only want to know how much of the original amount dissociated. So these are the dissociated amounts, they're equivalent. To get the percent dissociation, I'm going to have the amount that dissociated, so 0.00134, out of the original concentration. Wrong one. Alright, continuing on with more pH of weak acids and bases, we have calculating percent dissociation. Process is going to be incredibly similar. The only difference will be at the end. Instead of calculating pH, we're going to be calculating how much dissociated out of the original concentration. So then a percentage, so be times 100. So we're going to set up everything just like we had before. We need an equation, or for a reaction. Okay, we need our initial concentration, 1.0 molar, and then our minus and plus X's. So that would be our initial change equilibrium. Next step, of course, is to set it equal to the Ka. Ka is 1.8 times 10 to the negative 5th for the acetic acid. Again, will always be given to you. Equals X squared, hydrogen times acetate, over 1 minus X, the acetic acid. Relatively small concentration initially, pretty small Ka. Let's try taking it out. So if I cross multiply, that's just 1.8 times 10 to the negative 5. So I just need to take the square root of that. And I get that x is 0.00424. Okay. So again, if I wanted to find pH, I just take the negative log of that. I don't though, so I want to go ahead and do the dissociation amount divided by the original amount. Before I do that, I should probably check, make sure my 5% is okay. 1 times 0.05, well that's 0.05, versus 0.00424. I think that works out just fine. Our x is much smaller than our required value. So then I can say I've got the dissociated amount, which is the 0.00424, over the original 1 molar times 100. So I get 0.42% has dissociated. I'm just going to give you the answer for B. The setup will be the same, but be careful to note that you have a different concentration here. So once you solve it, hopefully you'll find that this should be, I think it's 1.34. It's definitely 1.3, but 1.34%. Somewhere close to that. Can pause it and solve that one. And then when you're ready, come back for exercise 4, calculating Ka from percent dissociation. Here again, very similar idea. You have a different acid, lactic acid, like in your mussels or spoiled milk. Not that they both are at the same time or anything, you know. It's okay. So C3H5O3 minus is our anion. We know that we start off with 0.1 molar lactic acid, none of these, and we're also told that we're 3.7% dissociated, which tells me that there is a relationship again between these two. If we sort of look at it in terms of the x's, as we normally do, then we can figure out what x is. 3.7% is really the same thing as 0.037, and if it's 0.037 dissociated, then that's some amount out of the original concentration, which was 0.1, which tells me what my x is. Multiply here, then x equals 0.0037, which then I can use to get all three lactate, hydrogen, and lactic acid concentrations and create my Ka. So 0.0037 squared. Best practice would be, since we know what x is, to go ahead and plug it in. 1 minus 0.0037. And then my Ka becomes 1.42, I believe it is, times 10 to the negative 4th. Because we're looking at sig figs here, we have a percent dissociation, or the concentration. This has fewer significant figures. You could get away with saying 1.4 times 10 to the negative 4 for your Ka without any difficulty, in which case it didn't honestly matter whether you subtracted from the original value or not, but it is the best practice to go ahead and do that.